Ladies and gentlemen, once again, thank you for being part of this webinar. In the rest of the session, what I'm going to do is share real experience of uh, of not just people like Brian and me telling ceramic is good. It's about people who have really embraced, really seen the benefits of ceramic systems on working water treatment plants. Before we start, um, I would like to throw light on uh, the, the UF technology and its relevance in all water applications. It has found, I mean, you would have seen that UF as a technology has found its place in all mainstream water applications like groundwater, seawater, surface, municipal. But when it comes to ceramic, it was mostly pushed into the industrial sector just because the water is complex. It needs heavy duty, heavy lifting, and the easy part was taken by polymeric. And it was branded that ceramic is more only relevant to difficult industrial applications. And in this session, you will see that's not true. UF is still UF, and the other applications can still take the best of ceramic membranes there. And we have, for this session, chosen some of the mainstream applications where our users have embraced this technology, looking at some of the key traits, which you will also learn in the session. A few to pick are ceramic filtration in drinking water solution, be it with well water, surface water, wherein we have rehabilitated an existing sand filter based plant. We've also seen that this technology has been doing very well in seawater pretreatment. And it's not just these lean waters. You will also see that this technology has found its place, very distinctive place in wastewater treatment, be it MBR or municipal wastewater. But before we get into these details, let's quickly look at what we really meant by value addition. How did we really see that there was value addition coming from this technology? In any water treatment, looking at the source, be it well water, surface water, seawater, treated wastewater. By treated wastewater, I mean biologically treated wastewater. Depending on the final use, there are a battery of pre-treatment steps that are in place. Modern technologies we see engages ultrafiltration, mostly polymeric. To protect this, there are a battery of filters upstream, which could be multi-grade filters or self-cleaning filters, and which is fed with clarified water, which is well conditioned with coagulation or softening or necessary oxidation upstream, which is well strained or checked for screens before it is entering the system. The value that we offer with submerged ceramic filtration systems is the replacement of the entire solids treatment system in the process chain. In some special cases where oil handling is done by process units like DAF, we found that not to be relevant, but that doesn't mean that we replace the DAF unit. But we've seen that it's in places where it's needed, we could manage even without it. As a result, you have a simplified single-step process chain, which results in a total cost of ownership. And the most important thing, which is most of the times not really looked at, is the reduced footprint, which also has significant cost in the capital savings. So now let's look at how we translated these benefits into some of these interesting references. To start with, drinking water. Well water seems to be easy. It is not orange juice. It's actually well water, fully contaminated with iron and manganese. It's not really challenging with solids less than 5 ppm, but the difficult part is the metals and the organics that come through. In traditional practice, the most common one happens to be ultrafilter or sand filters. But when the metals need sort of oxidation, the UF system, UF membranes, limited by their exposure to the oxidant, push back and give more space for the sand filters. In special applications, there is also need for coagulant, which also limits some of the polymeric membranes life expectancy. The expectations from these plants are to have absolutely low turbidity drinking water standards, rejection of virus, metal removal completely, and of course, oxidant tolerance. When you look at the existing solutions, which is the sand and the polymeric membranes do score most of it, but still fail at some of the key parameters, which reduces the overall life. While you see the ceramic scores checks all the boxes. So with these traits, one of our customers who had real challenges with high iron and manganese in one of their drinking water plants in the Middle East had failing RO system, which wholly relied only on sand filter as pre-treatment. The solution at the moment was to have an ultrafiltration upstream. And now the question is to have polymeric or ceramic. The key traits that were explored from ceramics were the ability to address metal scaling. Of course, the ceramic membranes also scale. It is not magic that it will not get fouled or scaled. It will get scaled. But the beauty is you can revive the membrane to its original permeability with necessary cleaning and not damaging or not deteriorating the membrane. And that is contributed by its high oxidant tolerance. In fact, there is nothing that really can oxidize it. So that's the advantage it shows. High filtrate flux means lower footprint. So that was also a requirement to fit into a very small space. And of course, the last two factors, which is robustness and consistent filtrate quality, is a no-brainer, which is part of any UF system that it must offer. So this plant comes into existence in 23 with what you see as a scheme here. No great pre-treatment. Well water directly goes into ceramic system with just provision for oxidation. The stripping is a natural process tried in these sites. And the benefits that the customer saw is significant increase in the RO's life. So there is no more replacements of RO. Thereby, the overall production cost and sustained operation is in place. We check one box now. In a similar application, let's go from under the ground to over the ground. But here, we have challenges with conventional systems. The problem with standard drinking water plants, which uses conventional sand-based filtration systems, is this. What you see in blue line is change in the filtrate quality from a sand filter, and the red line is the filtrate quality from the same feed, fluctuating feed from a UF. So any change in feed quality, the UF always ensures that there is consistent filtrate output. There would be a question, what if the pressure rises? And what you see here on the right is a change in the feed quality and the effect of the pressure shown by the green line and the consistent filtrate shown by the red line. So that answers that UF is a more relevant solution for drinking water, ensuring consistent output. But when it comes to polymeric membranes, the sad part is they are consistent, but they also need to have very stable feed. They're not robust, they're not chemically resistant, they don't have long life like what sand filters do. And now that's what is seen in ceramic systems. It's an amalgamation of both. It's robust, it's resistant, it has longer life. At the same time, it also delivers consistent filtrate quality with equivalent bacterial rejection and virus rejection too. And these traits were embraced in our next customer site. The problem here was a living or existing drinking water plant with limited footprint. It needed to increase capacity, but at the same time, it also had its share of problems with the quality. Fluctuating feed quality. During monsoon, we have really high solids coming in. And in some seasons, we have odor and color also coming in, which is not welcome in the drinking water scenario. And this was a fact that needs to be addressed. And the traits that were considered from ceramic, you saw a few in the past in the earlier slides. And the additional ones that were looked for was its suitability for drinking water. And that's the good news. All our ceramic membranes are suitable for drinking water. They are certified for drinking water. The second thing was it needs to fit into a very small footprint. It can be by virtue of higher flux, and it could also be by knocking off the demand for for additional pre-treatment like a clarifier and sand filter, which we saw at the start of the session. Besides this, robustness to handle fluctuations in feed and capability to handle extended scope of treatment beyond UF capacity. We call it ACLF, which is a process wherein we administer an adsorbent in feed, which can do filtration beyond standard ultrafiltration's capabilities in removing color, odor, or dissolved micropollutants such as PFAS. This project had a conventional scheme, as you see here, and the modification is reflected here. The addition that we were able to provide was almost 2 to 3 times in the existing footprint. At the same time, minor tweaks in the operation was allowing the whole plant to have the flexibility to deal with PFAS as and when it's detected. The plant was commissioned in 2025, and you see this is the scheme that it runs in. Surface water directly to UF with all provisions for oxidant dosage, coagulant dosage, and no pre-treatment such as clarifier or sand filter. The images on the left you see are existing sand filter beds, which was retrofitted with ceramic membranes in the same basin. So the customer was able to upgrade the existing sand filter basin within the same place, same footprint, add additional capacity to the existing one to draw as high as 160 mld. Even in case of high peaks of during monsoon, as high as exposure to 100 NTU, there were no challenges that the membranes faced. And it is also equipped with ACLF, which is active cake layer filtration, which doses activated carbon, which can ensure that most of the PFAS or geosmin, color, odor can be removed along with the solids that are entering the system. So we check the second box. Now from land, we go to sea. This is also a challenging application. For many years, this was an application where ceramic was never tested, but you will see how it has really rocked this place too. Similar to the surface water, the challenging parts of the feed here are solids, organics, and there's a little bit more, algae and oil. The heart or the core of the seawater treatment is the desalination system or the reverse osmosis. And whatever we see now is pre-treatment to the reverse osmosis. In studies done by Genesis in the past, show most of the plants suffer from deficient pre-treatment, which is mostly because of colloidal matter, biological material. And the reasons for RO failure are maximum, more than 50% relating to pre-treatment. Well, there are standard pre-treatments with sand filters, polymeric membranes, clarifier, which are as pre-treatment to the existing filtration techniques, but they're found to still be failing. In an exercise which one of our customers did, a large state-owned entity in Northern Africa, suffered from failure of RO, like we saw in the earlier slide, frequent RO replacement because of insufficient pre-treatment. Besides that, they also suffered from high TOC in feed and algae. The traits that were explored here were same as what we saw in the surface water treatment, independent operation for solids removal, ability to handle higher feed fluctuations, and also have algae mitigation, preferably higher flux to achieve lower footprint, and of course deliver consistent filtrate quality in all situations. The last was also modularity to ensure flexibility to add more and more capacity as and when that's needed, and you'll see how that translated in the real scale plant. What had really happened, when you look at this scheme, it was a conventional plant where raw water goes through a multi-layered treatment and then goes to a battery of pre-treatment and then comes to the desalination part. In the filtration section, due to lack of its performance, the best way to deal with this problem for improving the RO's life was to add a UF, which was an additional modification to the existing plant, which means additional footprint, additional OPEX, additional CAPEX. Whereas the scheme that was resulting because of modification by ceramic is this. We completely bypass the entire pre-treatment system there. Raw water directly goes to the ceramic and then directly goes to the post-treatment RO, whereby you have huge footprint savings and tremendous savings in terms of the pre-treatment operations. So this project was realized and commissioned way early in 2024, and it's been operating ever since then. You would see that the raw water, the seawater directly comes into the UF with just conditioning with coagulation. It has provisions for oxidation upstream to keep the biological fouling out. And we also have provisions to dose ultrasand to mitigate algae ingress. The nice part was we were not really dependent on it yet. We were able to manage the whole show still with the coagulant dosage. The outcome was this. They had a single stage pre-treatment to the RO, no more multi-stage management. So when you keep the UF happy, the entire system is safe. We were still able to manage peak algae exposure up to 40 micrograms per liter. Very high uptime. There was not much of replacement of pre-treatment to the RO, which means the frequency of replacement of the cartridge filters or the CIPs were much lower than what it was before. And the nice part is the plant is also going in for an expansion with a very minimal change in hardware. Just adding few more units on the top, solve the problem. Now we check the third box. Those were easy piece. Now let's look at the most difficult part, wastewater. MBR has found its space in water treatment for a very long time, and those were done by polymeric membranes. The most common problems that the operator see is when there is change in feed quality, there is change in throughput, pollen throughput, which results in frequent cleaning, which results in membrane breakage, and thus pollen quality or quantity, overall system failure. And that's more relevant to some of the limitations of former polymeric membranes, which needs protective pretreatment. They are vulnerable to break because exposure to harsh chemicals during cleaning or repeated cleaning definitely would break the membranes. And that's due to its lower oxidant tolerance. The beauty is these are all addressed by ceramic membranes. The robustness allow it to handle fluctuations in feed, and it is able to adapt. You can adapt the filtration fluxes, the operation conditions. You could call in for cleaning as and when it's needed. Does not really damage the membranes. It is robust and durable, which means it can take shocks during operation, and as well it can also handle wider range of chemical for cleaning. So in case you have oil, if you have an unknown foul, you can different cleaners and bring back its membranes permeability. And these traits were explored by one of our other users in Poland, in the food and beverage industry, where the problem was frequent replacement of membranes. So almost every 2 to 3 years, the membranes were replaced, which amounts to 60 to 70% of the filtration cost alone. As a result, the post-treatment, which was RO, also suffered bad. So when these two units are out, the overall operation of the plant is completely out. Amongst the several traits that you have already noted, the key traits that was explored by this customer was to have an adaptation to feed fluctuations. Of course, we saw this robust and tolerance to oxidant exposure, no-brainer with ceramic membranes. The requirement was the most important requirements to have it retrofit ready, meaning that you just pull out the existing membranes, put this, and ensure that it is running more or less with the same operation settings. And let's see what really happened there. After pilot trials, a successful trial, the customer did embrace this technology, induct this into their mainstream operation, and it's operating since then. And this plant was also expanded from the current capacity to almost double right now, wherein we see uh, the process is pretty much the same. Unlike what we saw with the surface applications where you have battery pre-treatment, after the biological treatment, it does go into the UF, but it's an MBR where the recycle happens. The operation is pretty much the same, but with conventional membrane polymeric UF. But the advantage is that you can have n number of cleaning as and when it's required. When there is fluctuations in feed, you can adapt the operational fluxes. You can change the recirculation rates and also ensure that the operation is not stopped because of necessary cleanings for the TMP changes. The advantage that the customer saw was it was able to replace the existing polymeric membrane one-to-one. And like we saw, there is no more replacements, smooth operation with coagulation whenever it's required, consistent filtrate quality, and no more downtimes. And the beauty is with conventional membranes, you need to lift them out from the tank, clean them into another tank, and bring it back. Everything is done in situ, and that gives good flexibility for the operators to take the plant down for a few minutes, clean them, and bring it back into action. And that's the advantage that this customer of ours saw. In summary, in all these cases, what you would have noticed, these were the 4 common traits that was embraced by all our users: ultra strong with no fiber breakages, tolerance to different level of fouling, say oil and grease, high TSS tolerance, and also high chemical tolerance. Extremely flexible. You have the game is just convert whatever is in the dissolved form to suspended and just filter them out. It is economical, which is what Brian explained to you, how it's proving to be more affordable with total cost of ownership. And of course, if there was no performance, we would have not been here with these experiences.